All right, so I am Jason Mielens, and this is joint work with Liang Sun and Jason Baldridge at UT Austin. And today I'll be talking about doing syntactic parsing specifically for low resource languages and some of the challenges and the interesting opportunities that we think those languages can present for doing parsing in general. I'd like to start first just by talking a little bit about what we mean when we say a low resource language and how that may be a little different than how the term is usually used or what you might think of it as. So this is just a figure showing the different data sets that we use in our paper. And you can see that we have a wide variety in terms of size. And for sort of larger, more established corpora, we're using English, Chinese, and Italian. But we're really mostly interested in the languages to the right of this figure, Kinyarwanda and Malagasy, which are two languages spoken in Rwanda and Madagascar, respectively. And so obviously a component of low resource languages is the fact that there's simply not a lot of data available for them, and that's what this figure is showing. But there's also an important part is that the data itself is substantially different than the data produced in a more well-established annotation setup, such as the ones that produced the Wall Street Journal or the Chinese Tree Bank. And so when you start looking at the actual projects that produce these things, you find that the data is substantially different, and it's not really the case that you can simply take a small section of one of these large corpora and use that small section as an approximation for a low resource corpus. We don't think that's an appropriate way to handle it, simply because the environments are so different. For instance, primarily based in the reasons that we think they're primarily different is based on the types of annotators you find in these setups. So in the small annotation projects, you're much more likely to encounter annotators who either have very little to no experience in the language itself. For instance, the two corpora for Kinyarwanda and Malagasy were produced at the University of Austin by our colleagues in the linguistics department. And each of those corpora were produced by a single non-native speaker of those languages over the course of about a summer. So it's really not a substantial amount of time that they've invested, and neither of them had any sort of computational background prior to doing that work. And we feel that that's probably a more typical annotator in the sort of low resource documentation type of annotation project, whereas the types of annotators for the Wall Street Journal and things like this have the benefit of usually being computational linguistics grad students or even faculty, and also just in terms of the guidelines that these things are working on, there's very little chance to iterate on this and have annotators produce a set of annotations and then discuss what worked and what didn't, and then you can go back and redo things and look for inter-annotator agreement and so on and so forth. That really doesn't exist in the small project world. It's really, you get what you have, and that's what you have to go with. You don't really get to go back and try to fix it because you just don't have that time, and you really need to focus on getting as much coverage as possible. And another thing that I just wanted to briefly mention on this slide is that some people have said, well, if we've only got a few hundred sentences, is it really worth it to make a parser? Knowing that it's really not going to be a fantastically accurate artifact that you produce. And we feel that the answer to that is certainly yes, because doing any amount of parsing is better than doing none, is more or less the story. And you can really stick this into, we were developing this in the context of using it in a machine translation setup for doing low resource machine translation. And we found that doing that is really helpful, even if the actual parser you have is not that great. And additionally, even linguists who aren't computationally minded like having this around. So some of the annotators, like I was talking about earlier, they liked having it just when they were doing their documentation efforts. They liked having it as a way to quickly generate or have it generate hypotheses about the syntax, even if they know that they couldn't trust it based on the fact that it wasn't that accurate or their analysis was different than the type of analysis it was producing. They liked having the sort of the thesis generator around, and then they could work with that. And of course, the canonical example for why you want a parser, even if it's not the greatest, is so that you can do some amount of pre-annotation and then have your annotator simply edit those as opposed to having them build it from the ground up. Because even in a low resource situation, more data is always better. So any way that you can have to quickly get more data is obviously going to be good for you. But when we look at this, this setup and the setup of the larger corporate, there's really a difference in the type of data, and that's what the primary difference we find to be. So in the sort of traditional setup, a tree bank is just that. It's a large section of great trees that you're super confident about. But in reality, in a low resource environment, you may only have a few trees that you're really confident about, and then you've got a bunch of other stuff that may be either partial annotations, sort of light bracketings for trees, or maybe even just part of speech taggings and things like this. Specifically because that's the kind of annotation that is easy to train novice annotators to produce, and to produce reliably. It's one thing to train them how to make a full tree, but if they can't reliably produce good annotations in that format, it's not really worth having them do it. So it may be, what you typically find is that you're able to produce a small number of really good gold standard trees, and then potentially a lot of other sort of partial annotations. So when we were considering the type of model that we wanted to use for doing this low resource parsing, we wanted to keep in mind this fact about the data. And in this work in particular, we're really interested in that sort of core small amount of really good full trees. And so we're focusing on that, but with an eye for the future being that we want whatever we select and whatever we work with to be able to incorporate as many sources of data as possible in hopefully a smooth and beneficial way. So when we were faced with that, we decided that a Gibbs sampler would probably be the most appropriate model, just based on the success that it has had in working on small amounts of data. So of course the way a Gibbs sampler works in general is that you have a set of objects. In our case, these are syntax trees from which you extract a set of parameters, in this case production rules like on the right, and then you use those to resample your objects. And this process repeats hundreds or hopefully thousands of times if you have the resources, until you eventually settle on what you find to be your final result for the trees. And luckily, a Gibbs sampler PCFGs already exists. It was done a few years ago by Johnson et al. And the way that it works for a single tree is a two-step process. First, there's a bottom-up approach, or a bottom-up phase, which is, it's the exact same as the inside table calculation from the inside-outside algorithm, where you basically fill in the chart moving upwards with the potential labels for the substring that these chart cells cover. And then once you reach the top, you turn around and then you sample downwards. So once you're at the root, hopefully it's an S representing a full sentence, and then you simply sample a split position as well as a label for the resulting subtrees. This then simply recurses, and you've, in no time, sampled a full tree. The problem with this comes when you start to add complexity. So the original paper on this dealt primarily with morphology, and in morphological parsing, your leaf nodes are morphemes and your root represents a word, as opposed to what we intend to do, which is have the leaf nodes be words and the full sentence be at the root. And the increasing complexity is due to the fact that even in the most polysynthetic languages, there are way more words in a typical sentence than there are morphemes in a typical word. And in addition, just the increase in the types of rules you find, there's a lot less right branching, or rather, there is a lot more right branching in morphology than in full syntax. So to deal with that increase in complexity, we were very much interested in the idea of latent annotations that have been shown to be very useful in variational Bayesian approaches, just to basically add in more meat for the parser to work with, more ability for specialization in the sub-symbols. So rather than just having an NP and having to somehow capture the idea of all noun phrases, by having it be a sub-symbol, MP1, MP2, you're allowing for the parser to find those interesting sections of noun phrases that can be referred to by a name. And so we wanted to try to combine this, the goodness of good Gibbs sampling for small data with this idea of latent annotations and produce a Gibbs sampler that worked with latent annotations. The problem with this is that you can no longer do the easy trick of simply extracting the parameters from your training tree bank, at least at first, because if you want to learn rules based on latently annotated sort of sub-symbols, you can't do that because in your training bank, if we assume this is a sentence from our training bank, those are annotated with the coarse, unlatently annotated symbols. Whereas you would really want something like this, where it's annotated with the different latent annotations. Luckily, you can do more or less the same, not trick, but the same Gibbs sampling approach to do the annotations for the trees in your tree bank as more or less a pre-processing phase. And then once you do that, it sort of reverts to the original problem. And the idea is basically that you run the exact same process. You work from the bottom up, building your chart, and then you sample downward, except this time, when you're sampling downward, you're no longer sampling a split position or the actual label for the node you're at. You're just simply sampling a latent annotation. You're holding the structure and the labels themselves fixed. So for instance, maybe you've sampled a 2 at your root node, and then now you sample the latent annotations for the children, but you're not modifying the structure at all, and you're not modifying the base label at these nodes. And again, this can just simply repeat down, and you've annotated your entire tree. And so again, once you do this, and now once you have your tree bank looking like this, you can use the exact same parsing algorithm from before to do this. It's just that now you have a bunch more symbols. So if we go back to the data that we've been using, you can see here we've got a wide variety in size, obviously, but also just in terms of the basic statistics of the corpora. This was important for us because we wanted to know what the parser we were building could do well, what it can't do well, and the consequences of that. So I'll split the results up into 2 sections. So on the large data sets, which again are not really what we were aiming at. It wasn't what we were aiming at, but it turns out that we're competitive with previous results even on these larger data sets. Although we aren't state of the art, this is still a good result for us because again, although the Wall Street Journal isn't really big anymore in the grand scheme of things, it's still big for us. So we're really not interested in these results as much, although we are glad that we are competitive. The great result for us comes on the small corpora, where we show a great advantage over previous methods by a wide margin in some cases. And so in addition to this, we were also interested in a number of other smaller experiments just on different aspects of the model as well as different aspects of just evaluation in a low resource setting. So the first thing we looked at was what benefit we were getting from the latent annotations. And so you can see here, as the latent annotation increase going to the right, you do get an increase in your F measure up to about k equals 16 for most languages. Once you get more that, or once you add more latent annotations than that, especially for the smaller data sets, you end up decreasing your score based on overfitting and things like this. A similar thing happens for English and Chinese once you go past k equals 32 at 64, for things like that. But in any case, there is still a point where it starts to head down. And the other thing that happens is that as you get a higher number of latent annotations, your computational complexity increases, and it's much harder to get the number of iterations that you need out of your Gibbs sampler to do this. So we developed, not really developed, it's a simple idea, but we found that it really helped us to do a sort of jump start or bootstrap type approach, where given your basic training and eval split, you simply select a very small section of your training set. We used about 5% for the larger corpora as what we call a jump set, and then you simply train maybe 1,000 iterations just on that jump set, and then you use the resulting model that you build from that as the starting point for doing full set iterations on your training set. And if you do that, you find that you really don't need as many iterations on the full set anymore, and you can achieve more or less the same result, but in a lot shorter time scale. Additionally, the other main point that we wanted to make was about unknown word handling, or sort of, I guess just low frequency word handling. It's really not unknown word handling. But we use a sort of clustering approach where you pick a frequency and then assign all of the words that occur less than that frequency to be unknown, and then you cluster those words based on context words in a nearby window. And then you train a classifier to predict the cluster for a new word, and that's how you handle that. But the thing that we varied, we didn't change the approach, we just varied what you trained on. So prior work and our work to compare trained the unknown clusters using the training set and the eval set to do the actual clustering. But we were interested in whether using an extra corpus, which it's a raw corpus that you part a speech tag, using that and leaving the eval set entirely untouched, not only just for the actual evaluation, but also for the calculation of your unknown clusters. And we found that it's about 3 to 4 points is the difference from leaving your eval set entirely alone, which is of course preferable. But the main idea that we wanted to convey was just that you really need to keep in mind what you're training on and what you're evaluating on, and what that means for you. So to summarize, Gibbs sampling for PCFGs with latent annotations is indeed a useful parsing technique, we feel. And in particular, small data sets seem to excel in this model. And additionally, latent annotations were very helpful and dramatically improved the results in all languages and all experiments. And we're also very much excited for the potentials this has for incorporating different data sources like partial annotations or dependencies, because it's a relatively straightforward notion to limit the chart, so you can exclude cells or require cells based on even just a single bracket that somebody is able to provide. So we feel that this is a very extendable model, and we're looking forward to future work where we look at that. So thank you, and I'll take any questions.
Yeah, once again, we have plenty of time for questions.
Yeah, I'm not sure if I understood correctly, but this Gibbs sampling with learning, it's similar, I guess, to expectation maximization. So do you also have similar guarantees about improving to global optimum?
No, there is no such guarantee in Gibbs sampling, I believe.
Okay, thanks.
Other questions? I had a couple of questions. In the unknown word clustering stuff,
Sure.
Do you end up with one just unknown Like, how many clusters do you have? And like,
Oh,
do
I'm
you
sorry, I forgot
use
to
sort
mention.
of,
10 to 20, depending on the size of the source corpus.
okay, and do you use orthographic features over the words as well, or just the context?
Yeah, so we use the context as well as just sort of basic, not actually morphological analysis, but the, 3 grams or whatever as pseudo.
Do you have the
morphs.
part of speech tagging accuracies? Do you know how well you do on part of speech tagging?
So we were using some prior work that we had done, and I believe it's about maybe 80%, 85%, 80%,
Okay.
depending on the corpus.
Okay. So it's pretty hard for the parser after that, basically, to build a parse tree.
Right.
Yeah.
Exactly.
And then, while I'm, of course, sympathetic to the idea of using latent annotations and constituency trees, what do you think about using dependencies? My experience lately has been that it's easier to annotate, and then potentially with the sampling technique, it could also go nicely because here, if you sample one bad bracket, then the rest of your sampling is really garbage. But with dependencies, if you have an arc-factored model, the arcs don't influence each other so much. So
Exactly. No, we're very much interested in that, and we are in the process of switching and doing dependencies with this same sort of idea, and specifically we're using graph fragment language, GFL, which is a sort of light dependency annotation scheme where people are free to annotate as much as they want, or to say, I really don't know what this is about, but I know it should be a bracket. And we're looking at ways that we can incorporate those and actually do dependency parsing.
cool. Yeah. That sounds great. Looking forward to it. Any other questions in the meantime? No? Okay, well, let's thank the speaker again.